This tutorial is about the basic characteristics of sound. It's just going to be a demonstration, but if you want to follow along, feel free. You can go to File, Open, navigate to Working Files, Multi-Track Session subfolder, and then double-click on 0201 Basic Sound. You might not be able to see the extension here depending on how you set up your computer. If you do see it, it's SESX, which stands for Adobe Audition Multi-Track Session. When you do that, you see all these clips here inside the multi-track session and all these files over here in the Files panel. So, what is sound? Sound is oscillations, vibrations, moving molecules. Those molecules can move through gas, liquid, or solid. So if I snap my fingers, that sudden shift, that sudden motion sends a vibration through the air, through those air molecules. Those air molecules vibrate up against my eardrum, and my eardrum translates those vibrations into my brain, and my brain says, oh, hey, he just snapped his fingers. Or if I pound the table vibrates and sends off vibrations through the air to my eardrum, and that whole same process starts again. If I put my ear up against the table, the sound will be different because the sound will be traveling through the table. It'll be vibrating not only air in my ear canal, but also be vibrating my skull, which creates its own kind of sound. So that's sound. Sound are these vibrations. Well, you can see vibrations inside Audition. Let me open up this file called Tone 440. And you're saying, oh, vibrations are a green rectangle. Well, no, I'll give you a different view of this in just a second. This is a 440 cycle per second tone. You've probably heard it before. This is the standard tuning tone. It was agreed upon by an international commission many years ago. It's 440 waves per second. And they settled on 440 as opposed to the 435 that was in the standard back then, because it's easy to divide 440 by 2. At least that's one reason why they did it. And dividing by 2 is an important thing when you talk about tone, and I'll explain that in a moment. I want to zoom in so you can see what's going on. So to zoom in, you just right-click here in the time ruler and drag a little bit, and that'll zoom in. Now you're beginning to see some differentiation here. I want to zoom into 1/10 of a second. There's 1/10 right there, so I'm going to drag across the 10th. There's 1/10 from right there to there. It's 1/10 of a second. So 1/10 of a second, if there are 440 waves per second, that means there are 44 waves here. And a sound wave has this up and down motion. When it's going up, it's pressing against your eardrum. When it's going down, it's pulling away from your eardrum. So this is this back and forth motion. And when it's very smooth like this, it creates that kind of electronic, boring tone. Like that. So that's A440, 440 cycles per second. And that equals this A tone. This A tone is the A above middle C, if you know your music, which is a little high for most men to sing and is kind of mid-range for women. But at any rate, it's A above middle C. Let me show you another look at these waveforms inside the multi-track editor. What I did was I created waveforms for the 440, and I cut that in half to 220 and 110 and 55, and then I doubled it to 880, 1760, 3520, 7040, and 1480. What this will show you is how the waves look different. When I cut it in half, the sort of magical thing that happens when you cut the number of waves in half is that it lowers the tone by an octave. I love how mathematics and music are so closely aligned. So we take this tone of 440 and we drop it by half to 220, and it'll be dropping by an octave. So I'll solo this first one. You can hear the 440. Let me go back to the beginning here. Here you go. Now I'll solo the 220, and it'll be an octave below that. And I'll solo it down to 110 to be an octave below that. And then I'll go down to 55. And that's just about the bottom, as far down as you can go and still hear it. The reverse is the case. We can go uphill as well. So if I go back to 440, bring this guy back to the beginning, go up a notch to 880, it'll be an octave higher. Go up another notch, double it again to 1760, like that. Let me show you this in a different view. I'm going to open up this thing called Tone Octave by double-clicking on it. It's going to look like that same rectangle you saw before, but I'm going to change the view to what's called spectral frequency. And now you can see that we go 440, 220, 110, 55, back to 440. Let's listen to what that sounds like. Now I'm going to jump ahead a little bit here. Right about here is where my dog starts going nuts when he starts hearing these high-pitched sounds. And now, when we get to these upper levels, We're going to get up to 7,040, and then we're going to get up to 14,080. And at 14,080, I'm guessing some folks watching this tutorial won't hear it. Did you hear that? I play this tone for my students in my junior college advanced video production class, and then I ask them to raise their hand if they heard that last tone, 14,080. And only a few students raise their hands, and they're almost always younger than 30. That's when our hearing starts dropping off, right around that time. And so we begin to lose the higher pitches. I want to show you how the waveforms look. So let me go back to that first multi-track session thing again. I'm going to go to the top. Turn off the solo for that. I'm going to expand the view here just so you get a sense of how this looks. See how the waves look for 55. You see that many, and then it's double the number of waves, and then double again the number of waves. Let me zoom in again so you get a better feel. There's 55, 110, and you notice how the waves are larger here and get smaller. When you decrease the frequency of the waves, you increase the wavelength, and so they're directly related to pitch. So you can see that we have a long wavelength here, and we have very few waves per second. So a long wavelength and a low frequency equals a lower pitch, and a smaller wavelength and a higher frequency equals a higher pitch. I want to show you one more thing, and then we'll wrap this up. I'm going to go back to the A440 tone again. I'm going to go back to the waveform view. Right now you're hearing this at what's called minus 18 dBFS. Watch this down here, and you see it settles at minus 18 dBFS. That's about 1/8 the potential for the full volume on this waveform editor. I can raise this by a certain number of dB, but what you're getting here though is when you look at this scale, you have see minus infinity and then 0 at the top. This dBFS stands for decibels below full scale. Full scale in Audition is 0, which is the standard way to do decibels when you're working with audio like this. So 0 means the loudest you can get inside this editor, and then minus infinity means silent. So right now we're at minus 18, which is about 1/8 the full volume. If I go up 6 decibels, the decibel is a measure of sound, then it goes up to minus 12. Now we're talking about a quarter of the loudness that's potentially here, a little bit louder. I'm going to go up another 6. It's now about half the potential loudness. I'm going to go up all the way now, another 6 all the way. That'll be as loud as you can get. Okay, so that gives you a sense of what amplitude is like. The higher the top value and the bottom value, the difference between the two of them, then the louder it's going to be. And then also the distance between them, the wavelength form, and the frequency determine the pitch. And that's your basic look at sound.